Okay, so thanks everybody for coming. Today we're happy to hear from Alex Lupsasca. He's been leading the charge the last couple of years, trying to determine what aspects of general relativity can be tested by experiments like the Event Horizon Telescope. And today he'll tell us about the observable shape of the black hole photon ring. So go ahead, Alex.
Thanks a lot for the invitation. It's great to be talking to this audience. Some of you may have heard me talk about the black hole photon ring before. So the first half of this talk will be a review of what the photon ring is for those of you who haven't heard. And if you know already, I apologize for the review. But in the second half, I'll focus on some more mathematical details of the shape of the photon ring and the precise observables we can measure. And I think there's some very interesting mathematical questions that may be of interest to this audience, and I hope will stimulate some more discussion. So to start with, obviously, as you all know, in 2019, the Event Horizon Telescope collaboration released the very first image of a black hole, the one at the center of M87, which is 50 million light years away. And I love this video from the EHT because it really brings to light how fantastic of an achievement this measurement is. So we've actually been staring at M87 for many decades, and we've been able to measure it with greater and greater resolution. And the EHT is only the latest image. The EHT's image is only the latest in a series of many photographs that have been taken of the galaxy, but it finally managed to resolve its core, where we saw this black hole in this now iconic image. So this is really a fantastic achievement if you think about how much you had to zoom to get this image. But of course, it's still a little bit blurry. And the big question is, of course, now that we've done this, we know it can be done. These photographs will only improve from now on. And the question is, what will we see as the technology improves and the photos get less blurry? And based on numerical simulations, our best guess as to what this image would look like at high resolution is something like this. So this is the result of a state-of-the-art GR-MHD simulation. That's General Relativistic Magnetohydrodynamics. So it's a simulation of the plasma around the black hole that includes the effects of GR and all the plasma physics that we know in some idealized regime. You can do more complicated things. But the striking thing about this image, and in fact, all the other images in the EHT data bank of simulations is that they share the same striking feature, which is this bright ring of light, which has come to be known as the photon ring. And what's very surprising about it is that as you vary the conditions in the plasma, which aren't quite known yet, as you vary the parameters of the plasma and the matter distribution around the black hole, you make these images and movies, but you always see this ring. And so that initially raised the puzzle, which is how come as we vary the conditions around the black hole, we always get this ring of light. And today, we understand that this ring of light is always there under some very mild assumptions, because it's really an effect of gravity and the way it lenses light. And so for the first half of my talk, I'll just review what we've come to understand in the past couple of years about this photon ring. In particular, I'll discuss what is its origin and how we can better resolve it. And finally, what can we learn from it? Now, just to give you the punchline ahead of time, as I said, this photon ring is a universal effect of general relativity. So it just doesn't depend on the details of the plasma around the black hole. It's purely governed by gravity. And it's got a very rich and intricate subring structure, which is entirely governed by new critical parameters that we've computed, gamma, delta, and tau, which are fundamental constants in gravity that we hope to measure in the coming decades. But I think in the more immediate future, we'll be able to better resolve this photon ring by having a space experiment, so doing interferometry with a space satellite, which would allow us to measure longer baselines, which is what astronomers used to refer to positions in Fourier space. And so the way we take these images is basically by measuring their Fourier transform and how long of a Fourier mode you measure depends on the separation between your telescopes. And so by going to space, we'll be able to have measurements of longer baselines, that is to say higher Fourier components of the image, which will let us resolve the finer features like the photon ring. And what I want to tell you about today is that the shape of this photon ring is actually, in the case of M87, supposed to be an ellipse, independent of the astronomical source profile. That's a prediction from strong field general relativity that we think we'll be able to test with very great precision using space-based interferometry. Okay, so that's the outline of my talk. And before I dig in, let me just say that this is an area of study that really started to grow in April 2019 after we got the image and we started to see this outline of a ring, which we haven't quite resolved yet, but we now think it's there and we're going to be able to see it. And so there's lots of questions about its properties and what's the best way to measure it. There are many, many papers and many more being written. And since this is a mathematics audience, let me just mention that this mathematician, Shui, had some very interesting papers on the mathematical aspects of the photon shell and its stability. There's actually 2 papers, and I think there's a lot more interesting mathematical work to be done in that area. So my own involvement with this actually started at Harvard, upstairs from the CMSA at the BHI. And with this paper, which involved a lot of astronomers and theorists, and actually Dan Kapitz, who's the organizer of the seminar. And the story I'm about to tell you, what is the photon ring and how can we understand it analytically, appeared first in this paper, and there's some additional details of what I'm about to say in these 2 papers, which I recommend if you want to know all the derivations. And the story starts with the photon shell. So everybody knows that a black hole has an event horizon, but perhaps what was a bit less known, not so much on people's radar before the EHT observations, is that the black hole has an other region outside the event horizon called the photon shell, in which gravity is so strong that light can be deflected so much that it goes around in circles, it orbits around the black hole. It's so deflected that it orbits possibly multiple times. But because it's outside the event horizon, it can of course still escape. And the 2 critical parameters, delta and tau, that I want to start by introducing can be easily understood as the azimuth swept, so how much angle delta phi a photon sweeps out as it bounces up and down in the photon shell, and tau is the time lapse incurred during a bounce, where by a bounce or a half orbit, I mean one half period from the bottom of the shell to the top. So at every radius in this photon shell, you have these bound orbits that describe these 3D trajectories. You can see them animated on Leo Stein's website, which I recommend you go to. It's very fun to play with them. And so as they go from the bottom to the top, or from the top to the bottom, that's a half orbit. They rotate by an angle delta, and that takes a time tau. So these 2 critical parameters are hopefully simple to understand. And then the 3rd critical parameter that I mentioned, gamma, is a little bit trickier to explain. So here it has its own slide. So of course, if you're in this photon shell, you're not automatically forced to go around on one of these spherical bound orbits. It's not enough to just be there. You also have to be aimed in just the right direction with the right momentum to stay on these orbits, on these shells. But if you imagine perturbing such a photon a little bit, so either you push it off its shell a little bit, or you change its momentum a little bit, these orbits are actually unstable. So the black hole traps light, but not stably. They're unstably trapped photons. And so if you push the photon a little bit, it's going to escape and either fall into the black hole if you push it a little bit inwards, or escape out to infinity if you push it a little bit outwards. And there's a Lyapunov exponent which characterizes the instability of these nearly bound orbits. And the way it works is that if you push off the photon a little bit, what you'll find is that in each half orbit, each time it bounces up and down, its radius, the deviation from its orbital radius, grows exponentially. And the exponent that characterizes the exponential growth per orbit, per half orbit, is this so-called Lyapunov exponent gamma. And like the other two exponents, delta and tau, it depends on the mass of the black hole, its spin, and the radius of the orbit. Okay, so I've introduced delta, gamma, and tau as fundamental parameters that are intrinsically defined in the Kerr geometry. Are there any questions about that? Okay, so now that I've defined them, I want to connect to observations that we can make here from Earth, and that is to say the images that we can see. So to do that, I have to introduce a camera in the screen. And so the way it works is that if you're a distant observer at some inclination theta, if you get a photon that reaches you with some momentum p phi p theta, then it appears on your camera at a Cartesian coordinate alpha beta. These are coordinates defined by Bardeen. Roughly, this is the intuition. So you can define an observer screen in this way. And then what you find is that there's a very special curve on the observer screen, which is known as the critical curve. And it's pretty easy to understand what it is. So if you aim a light ray directly at the black hole, the photon ends up getting absorbed. So the black hole is roughly around here. And of course, if you aim a little bit to the side of the black hole in a direction where it would miss if it were flat space, actually, because of the gravitational pull of the black hole, there's a sort of a larger region, has a bigger cross section. There's a larger region where the light ray actually gets pulled in and falls inside. But if you aim very far away, then the light ray might get deflected a little bit, but it can still escape to infinity. And so this critical curve is a special theoretical curve that delineates the region of photon capture, so the directions in which light rays are aimed and fall into the black hole, from the region of photon escape, which is the region where you send the light rays and they get deflected back out to infinity. And so what happens to these exactly critical photons that are exactly aimed on this curve, on this boundary curve? Well, if you shoot a photon here, what happens is it asymptotes to one of these unstably bound orbits. It's captured by the black hole and orbits in the photon shell in principle forever. And there's a lot of very interesting features about this. So for one, notice that every point on this curve is actually a sphere of different radius. So if you shoot a photon, say at this point, will asymptote to a particular radius in the photon shell, but then it'll explore that entire sphere. And the other thing is that going around the ring, around this curve in the image, is actually not going around the black hole in delta phi, but it's actually going in and out of the black hole. It's varying the radius. So that's really the warped nature of space-time in your face. And for the purpose of understanding the photon ring, we have to think about light rays that are near critical, that is to say, which are aimed just a little bit outside the critical curve, in which case they can go into the photon shell, orbit many times, and eventually escape, or light rays that are aimed just inside the critical curve, in which case they go around the black hole and orbit in the photon shell multiple times and then fall in. And I'm going to use the perpendicular distance from the critical curve on the screen, d, to characterize these near critical light rays. And the key relation that needs to be understood is that the closer you aim your light ray to the critical curve, the more orbits it can execute before eventually escaping or falling in. I'm going to get more quantitative about this in a second, but just understanding this already tells you that lensing by Kerr black holes has a very intricate structure, because what can happen is that a single source in the geometry can connect to a single observer along multiple light rays, which correspond to photons that circumnavigate the black hole a different number of times before reaching you. That has very interesting consequences. And to explore that, let me just flash this one slide to explain lensing, the structure of lensing in the simplest case. So let's imagine that we're an observer looking down at the black hole from the spin axis, and we have a light source in the equatorial plane. So we're looking down at an equatorial disk. In this case, the equations are very simple. What you find is that there's a direct image, which comes at you directly from the disk, this so-called n=0 light, because it doesn't orbit around the black hole at all. But then you can shoot light rays downwards that then go around the black hole, do a 1/2 orbit before reaching the observer. And then you can have a light ray that does n=2 half orbits, so a full orbit circumnavigates the black hole before reaching you. And then in principle, there's an n=3 and an n=4, and so on and so forth. And what happens is, if you have the image of the disk that arises from light rays that have gone around m times, it's very easy to describe what the next image is from light rays that went around m+1 times. And there's basically just 3 effects. So imagine the mth image of the disk is this color wheel, with this black line being the critical curve. The 3 effects are: 1, there's a demagnification. So the next image gets squeezed in closer to the critical curve, because remember, you have to aim closer and closer to do additional turns. And this demagnification tells you that the distance from the critical curve is exponentially demagnified by e⁻⁻⁰. So that's how the Lyapunov exponent that characterizes the instability of the orbits translates into a property of lensing, of lensed images. And e⁻⁻⁰ is smallest in Schwarzschild, where gamma is exactly pi. And so e⁻⁻ is about 4%. And as you increase the spin, this demagnification gets less strong, and at maximal spin, it's only about 9%. That's the first effect. The second effect is that the image is rotated, because as these photons orbit the black hole, there's frame dragging, so they also go around the black hole by an angle delta. Remember, that's how delta was defined. And so as a consequence, the image is rotated by delta. And again, in Schwarzschild, delta is exactly pi, so you get a half-turn twist in the image. But as you spin up the black hole, there's more frame dragging, and it can go up to 3/4 of a turn at maximal spin. And finally, there's a time delay, because it takes some time tau for the light rays to do an additional half orbit. And so you have to wait an additional time tau to get the image. And tau is roughly spin independent. It's basically 15, 16 amp. Okay, so you have this simple asymptotic relation that relates successive lensed images of a source, a large n. And it's already very good as soon as n is 2, which is nice. Okay, so I've explained the critical exponents in terms of intrinsic behavior of light rays near the black hole, and I've connected that to lensing properties of what you see as a distant observer. And so now let's take the final step and connect that to images of the kind that we see at the EHT. And so to do that, I just have to briefly explain ray tracing. So the way we make those simulated images, like the one I showed you at the start of the talk, is that for each pixel alpha beta on our image, we shoot a light ray back into the geometry, we evolve it using the null geodesic equation, and eventually gets close to the black hole, and there's a matter source around it, which has some emissivity. So there's some bright matter that radiates photons. It can also absorb them. And for each tiny affine length d sigma along the light ray, we update the number of photons on the light ray, that is to say the intensity that we end up observing, by an amount that's proportional to the emissivity. So the brighter the matter, the more photons we pick up. And in general, we must also account for the possibility that photons get absorbed. But at the frequencies at which we're observing at the EHT, the plasma that surrounds the black hole, we think has very low absorptivity, so we can basically ignore it. So every time you cross matter with some emissivity J, you add more photons. And when you do this in a simulation, you get the kinds of images that I showed you at the beginning. Now, the fundamental relation that I'm not really going to explain in detail, but I'm just going to flash here, is that in order to, you might ask, how many turns does a light ray execute as a function of how close it is to the critical curve? And basically from this relation that I showed you here, you can see that the answer is, oh, if I want to do n turns, I have to aim at a distance that's of order 1/gamma log d from the critical curve. I just inverted this relation. Okay, and so what that means is that as I aim a light ray closer and closer to this critical curve, as I take d to be smaller, the number of turns it executes the geometry is logarithmically divergent. And so this light ray is going to pass a number n of times through the bright matter in this photon shell region a divergent number of times, and every time it passes through the matter, it picks up more photons, and so the intensity should be proportional to the number of passes. And so what that means is that we should expect a mild logarithmic divergence in the observed intensity of light near the critical curve, because again, a light ray that completes n-half orbits through the emission region will collect n times more photons along its path. And so the photon ring, that effect that we saw in all the simulated images, can just be understood as this bump in the intensity, which contains the logarithmic divergence due to this phenomenon of light rays orbiting the black hole multiple times. And in the real world, nothing is ever infinite, and this divergence is actually cut off by absorption. So eventually, if the light ray goes around too many times, its photons get reabsorbed by the matter. But nonetheless, in our state-of-the-art GRMHD simulations, this remains a striking feature that dominates the images. Okay, so to summarize the story, here's a movie that just highlights everything I just said. So here's an observer screen, there's a black hole, and there are light rays emitted by the matter around the black hole that are only weakly lensed, that come at you more or less directly, and these form the direct or n equals 0 image of the emission. But on top of that, you can have light rays that are aimed just so, they're aimed into the photon shell in just the right angle that they can actually do a U-turn and execute 1/2 orbit, and these give you an n equals 1 image. And then if you aim even more carefully, you can, but you have to aim exponentially more carefully. So you can get light rays that do 2 half turns or a full orbit, but because this is an exponentially smaller region, you get an exponentially narrower ring on your image. And then when you look at the black hole in the real world, of course, you see the totality of these light rays at the same time. So the full image that you see is a superposition of these n equals 0, 1, 2, and so on and so forth contributions. And as a result of the lensing behavior, you get these additional lensed images that form the photon ring. And as I mentioned, this photon ring substructure has been confirmed in numerical simulations by George Wong. So here's the image I showed you at the beginning of the talk. We can take a horizontal and a vertical cross section through the image and look at the intensity. Those are the red and blue curves here on the right. And if you zoom in on the region near the photon ring, you can ask how much of this intensity comes from n equals 0 or n equals 1 or n equals 2 and so on and so forth photons. And what you see is that there's a background image, this wide shoulder here, which is the n equals 0 image, and then on top of it, you have yet again a lensed image of the emission in this n equals 1 hump, and then there's an n equals 2 hump, and an n equals 3, and roughly the height is proportional to n. They just keep increasing linearly because they're passing through the same region, picking up n times more photons, but they're getting exponentially squeezed by this factor e to the minus gamma. Okay, so to summarize the theory part that I wanted to cover, this is the general lay of the land. There's a photon ring. It's a prediction of general relativity that it should arise in images of a black hole and contain multiple subrings which are self-similar. They're just lensed images of the main emission with each subring indexed by the number n of photon half orbits executed around the black hole. And this phenomenon is controlled by Kerr lensing, which is completely characterized by 3 critical exponents, gamma, delta, tau, that respectively control the demagnification, rotation, and time delay of successive images. And the last thing I want to point out is that these photon subrings, they converge exponentially fast to this theoretical critical curve. But you can see that the n equals 1 is not quite there yet, and the n equals 2 is very close, but not quite converged yet. So the photon subrings, which are actually observable, converge to the critical curve, which is in itself not observable. It's a theoretical curve. And they converge to it, so they tend to have the same shape, but not exactly. So at n equals 1 and 2, there's already some deviation. Okay, so this was the summary of the theory part of the talk. Are there any questions so far? Okay. All right. Feel free to interrupt me, by the way, if anything is not clear. So So now I'm going to shift gears a little bit and try to understand what part of this story is most directly experimentally accessible. And last year, together with Sam Grella and Dan Maroney, we put out an experimental proposal for what we think is relatively low-hanging fruit. So measuring these critical exponents would be great, but seems fairly tricky because you need to measure multiple subrings of the photon ring to compare them, and we haven't even measured one yet. And so something that I think is promising, and hopefully will be done in my lifetime, is to measure the shape of the photon ring. And I think that could be used as a precise test of strong field general relativity. So a lot of the details of this proposal are in this paper, and there's relevant background in these other two publications. And a lot of the mathy aspects I'm going to discuss in the next 10 minutes are in particular taken out of this paper. So there's two major questions that we have to address. The first one is, how do we measure the shape of a bright curve in the sky? So we think the photon ring is this bright curve in the sky. What does it mean to measure its shape? How do we go about doing that? And the second question is, what is its shape? So okay, what is exactly the prediction from GR for the shape of the photon ring? And again, I'm going to give the punchline ahead of time. So the answer to the first question is that if you use interferometry, which is the experimental technique that's been used at the Event Horizon Telescope, it turns out that it's easiest to measure the curve's projected diameter as a function of angle, d var phi. So that is to say, as you go around the curve, ask what is its diameter at every angle. So imagine if you cast a shadow within the plane, what would be its width? I'm going to have lots of pictures to make this clearer, but that's the key idea. So it's hard to measure the actual physical shape that you would draw in 2D, but it's relatively much easier to measure its width at every angle. And so I think that's the first target for observation. And what is the shape of the black hole photon ring? Well, we found in this paper that in the case of M87, there's a prediction from GR that the n=2 photon ring, independently of the astrophysical profile, ought to have the same projected diameter as an ellipse. So as you go around the image, as you rotate the angle var phi, you should find that the diameter obeys this functional form. For some parameters R1 and R2, which depend on the astrophysical details, but the functional form of the projected diameter should obey this particular equation. Okay, so let me dig into these two things a little bit more. So this is a mathematical audience, so I'm not going to shy away from doing a little bit of geometry, but it's nothing too scary. It's just plain geometry. So the key is that if you have a closed convex curve in the plane, so here this is the sky of the observer, that's what you could keep in mind. It's possible to parametrize a closed convex curve by its normal angle var phi. So here, this is the point where var phi = 0 because the normal is horizontal. This is var phi = pi/2, var phi = pi, 3 pi/2, and then you wrap around back to 2 pi = 0. Okay, so it's very convenient to use normal angle parametrizations. And if you define the inward pointing unit normal, which I've shown here using purple arrows, and this is its formula, you can define something called the projected position f of phi by this inner product, and this is the particular mathematical form it takes. So it's going to turn out that if you're measuring curves in the sky using an interferometer, this is the quantity that you want to use to describe the curve, because that's what will directly connect to your astronomical observables. So why is this projected position useful? Well, first, this projected position, it really encodes information about the whole curve. So for instance, if you want, you can reconstruct the curve as a parametrized curve by inverting this relation to get this. So it encodes the whole curve, and it also encodes all other properties of the curve that you might care about. So for instance, if you care about the radius of curvature at a given point around the curve, there's a very simple formula for it in terms of the projected position. So from a mathematical standpoint, this is a nice way to parameterize curves. But again, the ultimate justification for caring about this is that it's going to come in a few slides where I connect to what an interferometer observes. Okay, so this might be unfamiliar to you. So what are some examples of curves and their projected position? So if you have a circle, well, a circle has uniform projected position, and it has uniform radius of curvature, and it has uniform width. Now, actually, it's a very old question that was first investigated by Euler, who asked, what are the curves of constant width? So it turns out that this technology is particularly nice to ask these questions. So here's an example of a curve of constant width. Here's the Rayleigh triangle. So if you ask what is the width of this curve at every angle, I'm going to show you in a few slides. The answer is this curve has the exact same width as this circle. So if you were to imagine that you were in 2D shining a flashlight and looking at the shadow cast by these curves, then obviously for the circle, no matter what angle you look at it from, it has the same width. And perhaps less intuitively, this Rayleigh triangle also has a constant width at every angle, which matches that of this circle. And I'll get back to this in a second. Now here's an ellipse, which has this projected position. And you can have more complicated curves. So here's a pebble, pebble shape with some random FFI that I cooked up. It just has to be periodic. And in fact, it doesn't even have to be positive. If it goes negative, then your curve is no longer convex. And in principle, you can deal with non-convex curves too. This is worked out in the paper, but I'm not going to go into it. I just want to point out it's possible to do this. But the interesting point I want to make, and this is again very important for interferometry, is that you can always decompose the projected position into two contributions, a diameter and a centroid. And that is, you can always take your projected position function, so your curve, and decompose it into a parity even part and a parity odd part. So D here is the parity even part, and C is the parity odd part. And then you can always reconstruct the projected diameter by adding the parity even and parity odd parts back up together. And geometrically, what is the interpretation of this decomposition? Well, the even part is the projected diameter of the curve, so how wide it is at every angle, while the odd part is just the motion of the centroid. So you can always do this shape decomposition. And here's an example. So this shape that I've drawn here can be obtained from this projected position. And you can decompose it into a diameter, which is 2 in this case, and a centroid motion, which is this little pentagram here. So you can always do a decomposition of the curve into a motion of a centroid plus a change in its width at every angle. And just so I don't lose your interest, what I'm about to tell you in a couple of minutes is that experimentally, when you look at a curve in the sky, it turns out it's very easy to measure its projected diameter, but much harder to measure the motion of its centroid. And what that means is that I think in the near future, certainly the first measurements of the photon ring shape will only access, it's almost certain that they will only access the projected diameter of the photon ring. So whatever the ring shape is, you can decompose it in this way. And this is the part, the parity even part, the projected diameter is the part that will be experimentally accessible. So I told you that the photon rings converge to the critical curve, but are distinct from it. Still, we can start out by asking, what is the shape of the Kerr critical curve? And so here I've drawn the critical curve for various values of the spin. So that's what the different colors represent. And I've decomposed it for you into a parity even part, which is a projected diameter, plus a parity odd part. And you can see here, I'm zooming in on the parity odd part. I'm showing here in numbers the scale of this line in units of the black hole mass. So you can see that these centroid motions are extremely tiny and we can almost neglect them. And so even though these shapes don't really look elliptical, the projected diameter part of the shape, if you decompose it in this way, does look very elliptical. So here's d of phi for all these different shapes. And here's the centroid motion. And the point is that this d of phi is basically the same d of phi as an ellipse. You can be a little bit more precise. It's really only elliptical at the inclinations that are relevant for M87. At very high inclinations, which are not relevant for M87, the curve gets more warped. And so then there are more visible deviations, but that's not really relevant for M87. Now, since this is a math audience, I wanted to point out that this Kerr critical curve has very interesting mathematical properties. For instance, this is not obvious at all, but it's defined by a degree 6 polynomial, so it's an algebraic curve. And in this paper, if you go to the appendix C, which is really for mathematicians, we computed explicitly what this degree 6 polynomial is. And we're not quite able to compute f of phi analytically for these curves in general. We were able to do it for an equatorial observer, but a non-equatorial inclination, I was not able to do this. So if there's a mathematician in the audience, this is an open problem. I pose it as a challenge. Can you take the curves that are defined by this degree 6 polynomial and compute analytically in closed form what the projected position is and then the diameter? And I think this can be phrased as a problem about the intersection of a line with the dual curve to this curve. So every algebraic curve has a dual curve, and effectively measuring the projected position is a problem that has to do with intersections of a line with a dual curve. So maybe this is helpful to get started. I would love to see somebody solve this problem in closed form, and I'm happy to talk to anyone who wants to think about this. Okay, so let me now connect to experiments. So experimentally, it turns out that this black hole M87, which is the largest black hole in our sky, along with the one at the center of our galaxy, Sagittarius A star, is still incredibly tiny. So it weighs 6 billion solar masses. It's actually bigger than the solar system, but it's so far away that it's tiny in the sky. It roughly has the same size in the sky as an orange on the surface of the moon, as seen from the Earth. So when you say, let's take a picture of M87, like the photo that we took, that I showed you at the beginning, that the EHT released, taking that picture is as hard as taking an up-close shot of an orange on the surface of the moon. So it's already incredible that we can even get a blurry image. And the way it works is not the way that your cell phone or your regular camera or your eye takes an image, but rather we're measuring the image in Fourier space using a technique called interferometry. And I'm not going to go into that. It's a complicated subject, but just as a cartoon, the way it works is that you have multiple telescope dishes on the surface of the Earth. They each measure the local electric field, so they collect photons. And then what matters is you look at the separation between the telescopes in the plane perpendicular to the line of sight to the source. That's the so-called projected separation. And there's an incurred time delay because of this projected separation, but you compare the electric fields with the appropriate time delay so that you're narrowing in on the same source. The measurements have to be phase coherent. And you define this correlation between these two signals, which is called the radio visibility, and it's a complex number. And it turns out that this complex visibility is really the Fourier transform of the image. This is called the Van Sittert-Zernike theorem in optics. And so basically the argument here, U, is called the baseline. It's just a point in Fourier space. It's the projected separation between the telescopes measured in units of the observation wavelength. So this is a dimensionless number. And so at fixed observation frequency, which for the Event Horizon Telescope is 230 gigahertz, this baseline length is just proportional to the separation between the telescopes. And you can see that if you want to completely measure the image, including its high Fourier components, you need to go to large telescope separation between them, so large U, to get the large Fourier components V of U of the image. So that's why we need to go to space if we want to resolve a narrow feature like the photon ring. And the key idea in the paper with Johnson and all that I mentioned in the beginning is that if you go to baseline lengths that are in this regime, so you imagine you have a ring. The ring, of course, is not an infinitely thin curve. It has some width, but the width is much smaller than its diameter. So in units of the black hole mass, the diameter is roughly 10 m, and the width is less than m. So there's a large separation of scales. And if your telescope separation is large enough that you're in this regime U, where you're much bigger than 1 over the diameter, so your telescope, your interferometer is able to resolve the ring, the fact that there's a ring, but is not able to resolve its width, then basically it looks like a narrow curve, like those idealized closed convex curves I've been discussing. And in this case, you can show it's an exercise in a Fourier transform. In Fourier theory, that the Fourier transform of an infinitely narrow curve, if you take I of x to be tracing an infinitely narrow curve on your screen, the V of u that you get takes this form. Okay, so this looks maybe a little bit scary. It's a complex quantity. There's an overall phase, which depends on the projected centroid. And then there's 2 modulated signals, which oscillate with a frequency that's set by the projected diameter d phi of the curve. Okay, and the coefficients here, which control the modulation, are fixed by the intensity around the curve. So here's the image that you have. You pick a var phi, you pick an angle around the image, and then corresponding to that, you get a projected diameter of the curve, a centroid displacement, and an intensity at the leftmost edge and rightmost edge of the curve. That's alpha left, alpha right. And these 4 things, alpha left, alpha right, d phi, and c phi, tell you exactly what the complex visibility is along that direction in the Fourier plane. So for baselines at an angle var phi. And so if you go to long baselines, so you're in this regime where essentially the photon ring looks exactly like a narrow curve, then this visibility has the feature that it oscillates with a period that's set by the projected diameter. Okay, so it turns out for experimental reasons that measuring this full complex visibility is very hard. And why is it hard? Because to measure the full complex visibility, you have to keep track of its phase. But keeping track of the phase means that you have to know exactly what the extra path length that this photon had to travel along compared to this photon is. You have to know this tau g very precisely. But these photons, when they cross the atmosphere, they can bounce in raindrops of water. Or even the cables in your telescope, as it heats up, because it's some complicated piece of electronic machinery, the cables can dilate. And so the photons have to travel additional phase cycles. And these tiny little perturbations mean that it's very hard to know what this time delay is exactly. And so it's hard to measure the phase exactly. And so it's very hard to measure the centroid exactly. But if you only care about the amplitude, so the norm of this complex quantity, which is called the visibility amplitude, that's much easier to measure. And notice that if you take the amplitude of this quantity, then the centroid completely drops out. And you're left with this formula, which depends only on the projected diameter. Okay, so to tie everything back together, any shape in the sky, if it's narrow enough, you can view as a infinitely narrow closed convex curve. You can decompose it into a diameter plus a centroid. And it turns out that if you have an interferometer, it's much, much easier to measure only the diameter, because that only requires you to measure the visibility amplitude. And if you wanted to measure also the centroid, you would have to keep track of the visibility phase. And the phase information is hard to extract because of the atmosphere. Okay, so what that means is that an intensity interferometer, which is what an interferometer is called if it measures visibility amplitude only, can measure shape information, but it can't tell the difference between, say, a circle, which has constant diameter, twice the radius and no centroid motion, and this shape, which is called the Rouleau triangle. Again, it was, I think, first investigated by Euler, which has the same projected diameter. At every angle, it's a constant, which is twice the radius of the circle. But this guy has a non-zero centroid motion. So these two shapes have the same projected diameter, but differ only in the centroid motion. And actually, that means you can make a bicycle with wheels that are Rouleau shaped, and I think such things exist. But the point is, visibility amplitude alone cannot tell these two things apart. So the low-hanging fruit for an experimental measurement, which is to access only the visibility amplitude, and that is to say, it's to measure the projected diameter of the photon ring. And I think that's what we're likely to be able to do first. And that will give us a lot of information about the shape, but not full information about the shape. So we'll be able to redraw it up to the kind of difference that separates the circle from the Rouleau triangle. And what we found is that the projected diameter of the n equals 2 photon ring for M87 is basically that of an ellipse. And so an ellipse with radii R1 and R2 will have a projected diameter that obeys this functional form, and that's what we expect to see for the n equals 2 photon ring. So let me just point out something that's very interesting here. This photon ring and its substructure offers a natural separation between astrophysics and general relativity. Because remember, when you look at the image, you see the direct emission, this n equals 0 light that comes at you directly, and that obviously depends on the nature of the source. You're seeing whatever is around the black hole, whatever plasma is there. So that's completely non-universal. It depends very much on the astrophysics. But once you know the n equals 0 background image, the photon ring pattern, this lensing pattern of images that are stacked on top of the main emission is completely universal and follows from GR. It's just composed of these exponentially demagnified images of the main emission. So when you look at the image, there's a separation between whatever astrophysics you get in the background and the photon ring lensing effects, which are universal and appear near the critical curve. And likewise, the separation between astrophysics and general relativity carries over in Fourier space, which is what we directly access with our interferometer, because all the astrophysical effects, the background, is important at short baselines, which are very sensitive to exactly what's around the black hole. But once you go to long enough baselines, you're really only seeing very narrow features like the photon ring, which is lensed. And of course, in principle, there are other narrow features, like you might have these transient astrophysical flares that pop in and out. But the point is, those are transient and should come in and out of existence. But the only very narrow feature that should subsist over long time scales ought to be the photon ring, which is always there because the black hole is always there and it's always lensing light. And so by going to long baselines, you can separate out the universal effects of general relativity from the astrophysical effects, which we see at short baselines that are accessible to us with the EHT. So I think one lesson that I want to convey is that if you want to probe gravity with black hole imaging, you want to get into this photon ring physics regime, you have to go to long baselines, and then that'll naturally happen. But you need to go to space for that. So to summarize, can we test general relativity by measuring the photon ring shape? Well, that's really asking two separate questions. The first one is, does this clean separation between astrophysics and general relativity, between the short and long baselines that I've just described, actually happen in realistic models? So can we test GR in principle? And there's a separate question, which is it possible to achieve the experimental precision that would be required for an for an interesting test. So can we actually test the theory in practice? And without going into all the details, because this is very heavy on numerical computation and astrophysics, the answer to both questions is yes. So for the first question, we investigated 100 models of different astrophysical plasma around M87. We found that in all these models, the n=2 photon ring diameter can always be measured from its interferometric signature. So you go to long baselines, you get this ringing pattern with a periodicity that's fixed by the diameter. So you measure the ringing, you get the periodicity, which tells you the diameter at that angle. And so if you measure the complex visibility at every angle in the Fourier plane, which you can do by having a telescope orbit the Earth, then you can measure the diameter of the photon ring at every angle, and it ought to be that of an ellipse. So it has to obey this shape independent of astrophysics. And on top of that, we think that this is an experiment that can actually be done in practice. And Dan Maroney, who is a co-author of mine and a leading expert in these experimental observations, has given some thought to how this can be done. And you need you need a satellite with some pretty fancy technology, but it's not science fiction. This is something that we think we could do. And we ran a forecast of the experiment, and we found that we think in principle it ought to be able to test the shape of this ring and therefore perform a strong field test of general relativity and of the Kerr hypothesis to incredible precision. I can go into the details of how this goes, but I just want to flash the overall big picture. So what are we saying exactly? We're saying, imagine you have the Earth here and you put a satellite in space and it orbits around the Earth in the plane perpendicular to the line of sight to the black hole. At every angle var phi around the orbit, you measure this visibility. And because if you put your satellite roughly at lunar distance, then the baseline length will put you exactly in the regime where you see the n=2 photon ring, and that's what dominates the signal. And so by doing that, you can measure this ringing in the visibility amplitude, and its periodicity tells you the diameter of the ring. So as the satellite orbits, at every angle var phi around the orbit or around the image, you measure the projected diameter of the image. So it's the width of the ring. And the prediction from general relativity is that this diameter should obey the same form as an ellipse. So it's this functional form, which we plotted here. And we made a forecast for the kind of experiment that we think would be doable. And in our simulated experiment, we got data points that look like these. And so we concluded that it would be possible to perform this test. And if you haven't never looked at a data analysis of experimental data points before, this is actually like an incredibly good result. So we think this could be an amazingly stringent test of general relativity. So that's the big picture. And I always like to end this talk with this discussion of whether we need to test GR. So I think everybody in this audience works on GR and thinks about gravity. So maybe I'm preaching to the choir, but why is this something that's worth doing? I think, scientifically, we know that GR should fail deep in the black hole interior. However, there's absolutely no reason to expect a breakdown outside. But the event horizon is a visible edge of the observable universe. You literally can't peer beyond that. And these photons that appear in the photon ring, they've come as close as possible to the event horizon and still reached us. They orbited around the black hole and probed its strong gravity. And so I think if there is a deviation from general relativity outside the horizon, this is a really good bet for detecting it. And it should lead to changes in the shape of this ring, which sensitively depends on the gravity of the black hole. And we obviously think it's a Kerr black hole with a Kerr photon shell, but this prediction has never been directly tested. LIGO has started to put some bounds on this. They're not very precise yet. I think they've quoted tests of GR to the 4% level, which is already, amazing. And we had nothing before in the strong field regime. And obviously they're going to continue to put tighter and tighter constraints. But this is a different window into Kerr black holes, because LIGO is measuring the dynamical regime. You have two black holes merging, and the space-time is dynamical. It's a violent merger. Here, this is a different corner where we're probing the pristine gravity of a single black hole. And so this Kerr prediction, I think, has to be thoroughly tested because it underlies a huge amount of astrophysics and also plays a driving role in theoretical physics. And it's just good science to directly test important assumptions that impact multiple fields. And the last thing I want to say is that a lot of people talk about testing GR, but I think a real test has to have the possibility of changing minds. That is to say, to have a real test, it has to be possible for you to be surprised. And the problem with just looking at the astrophysical conditions around the black hole is that if you see something that doesn't match one of your simulations, you'll never conclude that GR is wrong. It just means your astrophysical conditions that you assume have to change. But it's very hard to imagine that you would ever conclude that you got GR wrong instead of the astrophysics. But if you measure the photon ring, because its shape follows purely from GR, well, then there's no escape. If the ring is not the shape predicted by GR, then GR has to be wrong. And I think that's why this is a very sharp and exciting test of gravity. Okay, I think I've said enough. I'm just going to stop here and love to take questions. Thank you.
All right, thanks for the fantastic talk, Alex. Do we have any questions?
Yeah. Yeah. So you talk about the testing strong field GR near the horizon, but I'm kind of confused about that, since especially for large black holes, you can have arbitrarily weak curvature near the horizon. So yeah, could you say more about that?
Yeah, I mean, I'm not, well, okay. So my private feeling is GR holds all the way deep into the black hole interior and only fails right near the singularity. I mean, I think that's what most theorists believe, and there's good arguments from effective field theory to support that. But it's also arrogant to think you know the answer about everything before you go out and see the world. And black holes are the most extreme, mysterious objects in the universe. I think we just don't know until we do the experiment. And the other thing is, I'm convinced that, unless mankind disappears because we kill each other in war or famine or whatever, there's no way people are not going to be curious enough to image black holes and measure them more precisely. So I think these are experiments that will be done anyway. And I'm trying to convince people to do them sooner rather than later. I'd love to see the results in my lifetime and before I'm old and gray, if it's possible. And I think it's really interesting. I mean, yeah, although all the evidence suggests that you won't see a deviation from GR, well, maybe you go do the experiment and there's a surprise. And of course, we can't see inside the event horizon. All I'm saying is you can't see inside the event horizon, where we know gravity fails. GR has to be modified. But this region is just outside the event horizon. And the photons that orbit here, they really probe the gravitational field of the black hole right outside the event horizon. This is the visible edge of the observable universe. So it's as good as you're going to do with imaging. So let's, it's the best we can do, and let's go and do it. That's my attitude.
Thanks. Yeah, and then a follow-up question. Do you know, or have a rough estimate off the top of your head, how the like Kretschmann scalar at the event horizon for these gargantuan black holes compares to like the surface of the Earth?
I have no idea, but I mean, it diverges like 1/r⁶, if I remember correctly. So it's, if you make the black hole arbitrarily large, it's arbitrarily small at the horizon. I think that's how it works. Yeah. Why is the Kretschmann scalar that important, actually?
Oh,
That's something I've
it's one of the simplest
tests of curvature
scalars you can make.
singularities. Yeah.
Yeah, I suppose I could have asked about Ritchie's scalar for what I'm thinking about right now also.
Do you have a sense for optimistic timeline for measuring the n equals 2 ring?
Yeah. Okay. So I think my thinking has evolved a lot on this, and this is obviously something I'm talking to a lot of people about all the time. So the thing we're gonna get next is NGEHT, which is the upgraded version of the Event Horizon Telescope, and the timeline, the optimistic timeline for that is that it would go online in 5 years. It's probably going to take longer actually to have the full array, but it's not a binary thing. It's not on or off. It's going to be more gradual. However, it looks like the current plan is to stick to the Earth because it's much cheaper and the technology is more tested. And so I think it's very likely that just with Earth telescopes, but having more and more telescopes on Earth, what you're going to get is better coverage of the Fourier plane and less blurry images, but not necessarily being able to resolve higher features. So I think the answer is for the n equals 2 photon ring, it's probably pretty far out. Heino Falki in Europe has submitted a proposal to the European Space Agency for a large flagship mission to do this. There's a paper on the archive with the details. And I think the proposed timeline for that, the next time slot for that is 2050. So that's, I'll be in my 60s by then. But I hopefully. And so I think n equals 2 currently is far out. The Russians have a proposal called millimetron, which would actually let you see n equals 3 because they want to send a satellite to the Earth Sun Lagrange point L2, which is really far. And they have a pretty mixed track record. So they had some missions where they were 20 years late, but they've caught up, and now they're on schedule, and their timeline for this is still 2029. It's not slipping. There was just a talk about this this summer at the Max Planck, the Marcel Grossman meeting. So they seem really serious about sending something up in 10 years. I don't know, but it's probably going to be toned down a little bit, but it's so ambitious. If they do even half of what they say they want to do, that could be really good. And I think what's really the next step is probably the n equals 1 photon ring. And I think that one, it's almost visible in the 2019 EHT data. So the 2019 image, but it was 2017 observations. And so the n equals 1 photon ring is just around the corner. It could be that just by sticking to the Earth, but cranking up the frequency, which will also increase the baseline, you might be able to see the n equals 1 photon ring or get some data points. So some detection. And I don't see why some kind of faster mission in Earth orbit wouldn't let you measure it better. I think there's various proposals being discussed for that. So the timeline is, I think, any definite plans for n equals 2 don't really exist, or they're still far off into the future, with the possible exception of this Russian plan, which could happen. And I think we're probably nothing in the next 5 years, but maybe with NGHT, we'll be able to see n equals 1 or some related mission. And I think n equals 1 is already really interesting. I mean, n equals 1 would give you a qualitative test of GR because you'd see photons that did execute a U-turn around a black hole 50 million light years away. I think that's really cool. But I don't think, but the n equals 1 photon ring shape is still dependent on the astrophysical details because you're not yet in the very strong lensing regime. So it's, I think scientifically it's less, it's not as sharp or stringent a test of the theory, but it's probably the next step and still hugely exciting.
I just want to mention a little history. If you look at MTW from, of course, that book was written in 1973. You'll see a little numerical calculation of some of these orbits around Schwarzschild. I forget what chapter this was based on some modeling of Wheeler and Dickey, of course, very historic characters, but
Right. So okay, I think the history of this is really interesting. This paper, I think, computes the Kerr critical exponents for the first time. So Kerr
Right.
was neglected for a long time because it's technically harder. But the Schwarzschild story goes back, I think. So this is kind of a fun topic for historians, and I keep getting those emails. I keep getting emails with papers that are earlier and earlier. And so actually, there's a 1917 paper by David Hilbert where he computed the critical curve. He computed the shape of the critical curve for a Schwarzschild black hole, or already, this is over 100 years ago. And I think Darwin, the grandson of the famous Charles Darwin, was a physicist. I think he computed the critical exponent e to the minus gamma, the demagnification factor,
yeah, I don't think though. I mean,
in the 50s. And then Lumine understood the story. Lumine understood the demagnification back in the 70s for Schwarzschild in detail. So it's true, the Schwarzschild story has been known for a very long
Right.
time. Yeah.
Yeah, but you will see that in MTW. This little
Yeah.
calculation of that based on Wheeler and Dickey.
Okay, great. Do we have any other questions? All right. If not, let's thank Alex again.
Thank you.
And we'll see everybody next week.
Thank you.